So I'm going to give a talk about the equations, so y'all can ignore this and keep looking at the model if you wish. Those that are interested in the foundations of the code and what's going on, I'm going to try to figure out how to share screen. All right. So I've spent a lot of time in your position with MOM6, especially many years ago, and trying to understand the equations, to understand the method, and understand how to diagnose stuff in the code. My guess is that 99% of you are not going to care about the algorithm stuff that Hallberg talks about, but you're going to care about the equation stuff that I talk about. Because you're ultimately going to want to look at the output and understand what you're getting. And you're going to hopefully trust that everything that Bob and Alistair and others have done to develop the algorithms is good. The 1% of you that get into the code and try to muck around with the algorithms, good for, you're the ones that are priceless, the ones like Bob and Alistair. The ones like me that are interested in a using of the code, we're dispensable, but we are also important and we need to know what we're doing. So if you want to understand the documentation of the code, there's lots of different pieces and they're kind of spread throughout. We're trying to consolidate and make the code more documented from a user perspective. So first thing, go to Google, type in MOM6, what comes up? First one is the MOM6 repo. The one that I want to highlight to you is the MOM6 examples. It's a sort of super repository that has a lot of the examples. In there is this link to Wiki. Now, I think most of you know that Wiki is something that you can edit. And we really encourage people, especially new users that are coming in and find questions that are not answered, but you find the answer, to please leave breadcrumbs behind you for others to follow you. That's really how the documentation it gets built up, with users coming in, providing test cases and providing fixes to the technical docs or to the documentation. So then under the wiki is technical docs. And there's many different pieces here, one of which is source code documentation. And that's what I'm going to talk about now. I'm going to talk about a slightly updated version that I've been working on the last few days. That is going to be what I'm going to lecture on. So instead of the main, it's on the repo dev GFDL. It will get updated to the main soon enough. So the equations, the documentation of these equations is really done by Kate Hedstrom, who put together a lot of this material months ago, pulled together from different papers and different pieces around the literature. I went in and did a bit of editing of this over the last few days. So it's 95% Kate's and 5% mine. And if you find bugs or find things you want to enhance, this is a wiki. You can make changes. Well, you can, this is on GitHub. You can make changes to this piece. Drop the link. The whole point is you don't have to remember links. It's Google. Okay, let's see. You're right. So I'm going to talk from, this is the one. It's under the dev GFDL branch. Yeah. Thank you, Sonia. I forgot about that. Now I have to find out where I am. Okay, so you're not seeing my chat window. So this is the governing equations of the model. How do I stop that? It's a Boussinesq, it's a hydrostatic model, and it has a non-Boussinesq or Boussinesq option. And the documentation here is just to be simple, following the Boussinesq approach. It's very analogous to the non-Boussinesq. So, and these are written in Cartesian coordinates, and I'll go down to the generalized vertical coordinates in a few slides. Horizontal momentum, hydrostatic, continuity, tracer for temperature, potential temperature or conservative temperature, salinity, in situ density, and velocity. I'm going to be really, this is not a class in GFD. I'm just going to be very quick. Material time derivative, writing everything in terms of flux form, which we do. Flux form is the starting point for any discretization for finite volume, flux form tracer equations. And the vector invariant form. Now, this is something that I had to learn when I came in, because MOM5 and MOM4 were not vector invariant. ROMS is not vector invariant, whereas MIT GCM is, NEMO is, MOM6 is vector invariant. You do a continuous identity where you change the material time derivative on the velocity, and you introduce the vertical component of vorticity, zeta, and you introduce the kinetic energy per mass, horizontal kinetic energy mass, and write the velocity equation in this form, where you have the pressure plus the kinetic energy on the right-hand side, and the geopotential for gravity. On the left-hand side, you have the absolute vorticity, F plus zeta. Okay, and all the other equations are the same. This is hydrostatic, continuity, tracer equations, and the equation of state. So that's the first page, that's governing equations. The second page, now, generalized vertical coordinates. Let me do this. If you want to follow along, I will chat this one as well. So MOM6 is written in generalized vertical coordinates. I would say in the community, the international community, the top people in the whole world on generalized vertical coordinates is Hallberg and Adcroft. And the MOM6 is the sort of peak of the technology for generalized vertical coordinates and the vertical remapping method, which I'm going to talk about in a few minutes, the Langrangian vertical remapping method. So it's a straightforward transformation, straightforward mathematically. You transform to R coordinates. R is a function of X, Y, Z in time. That's your generalized vertical coordinate. Examples of that are isopycnals, terrain following like we have in ROMS, pressure for a non-hydrostatic, for a non-Boussinesq model, or Z star, which is what we had in MIT and MOM5. So a few changes are made, but not a whole lot. The velocity equation appears, and this R dot is a sort of pseudo vertical velocity. It's a material derivative of the vertical coordinate R, and it acts like a pseudo vertical coordinate. And pressure coordinates, that would be pressure dots. So you'd be moving across pressure surfaces. And it appears throughout the tracer equations, and you now transform a continuity equation from a non-divergent condition on the three-dimensional velocity to a time-dependent thickness equation, okay? Where Z sub R is a partial derivative of Z with respect to R. Some people call that specific thickness. Some people just call it thickness. If you then do a finite volume integration over a layer, now this is now starting to discretize in the vertical, we introduce thickness, real thickness in meters. Okay, and it's the symbol H. H is a thickness integrated over a layer of the specific thickness, integrated with respect to R, your vertical coordinate. When you do that, these Z sub R terms appearing in the continuous equations become H. Okay, actually there should, and except in a couple of spots, they become H in most spots. Like we have the thickness equation. And these R dot terms, they correspond to transport across R surfaces. We call those diasurface transports. If it's an isopycnomolar, it would be diapycnal transports, okay? And that is the stuff that moves material and momentum properties across your coordinate surfaces, okay? All right, so another thing to note, when we do, well, let me go to the next slide before I jump ahead. Let me now move to the method that's used to solve these equations. Let me chat this again, because these have yet to be updated on GitHub, so you won't find them unless you know the link. So the vertical Langrangian method, or the vertical Langrangian regrid remap method, is what MOM6 uses to solve and to time step its equations. And so Langrangian, I think we remember what Langrangian fluid mechanics is about, where you follow fluid elements and and from a computational perspective, you time step your fluid motion by following the motion of a fluid parcel or fluid element. And there are actually there are methods out there, there are codes out there that do that in 3D. And so you So here's a schematic of that. You have a square region of fluid and you lay down some grid, some, call it, XY grid, and you allow that fluid patch to move. It's a small fluid patch, and it gets bent and contorted around, right? And so if the grid lines are sort of pasted onto that fluid region, they get contorted as well. Now, there is a need, and I think if you did any Lagrangian mechanics, you probably remember that at some point, these fluid elements will get so contorted, they'll rip apart and you lose all continuity of your ability to maintain smoothness of your properties of your grid. So you have to do a regrid step. And that's a sort of coming in and regridding. And when you regrid, you have to then map your fluid properties onto the new grid, the regridded. So there's a regrid remap step. All right. So MOM6 is not 3D Lagrangian, it's 1D, just in the vertical. Okay. The horizontal is still Eulerian. It's still, but it's a quasi Lagrangian, or it's a vertical Lagrangian regrid remap method that we use. So from an equation perspective, what is done is that we time step the model in two main steps. The first step, all these points in the code, in the equation where you see an R dot, you have an R dot in the momentum equation or the velocity equation, the thickness equation, the temperature equation, and the salinity equation. You set those, you ignore those. You don't set them to zero. You just don't time step with those terms in there. You time step with everything else. And what that is a stacked shallow water model effectively. Okay. Because you're ignoring all cross grid transport. So it's like you have these immiscible stacked shallow water layers. With one caveat or one exception, the right-hand side terms, these mixing terms, these vertical mixing, the diabatic processes and the temperature equation and the dihalide processes and the salinity equation, you don't set those to zero. You time step as with those terms on the right-hand side as well. Okay. So that's the first step. You could think of it as the Lagrangian step, right? Because you're moving, you're time stepping as if there's no transport of stuff on the left-hand side, at least, across these layers. All right. And then the next step is the regrid remap step, which brings in these R dot terms. Okay. And that's a step that is not written continuously. It's something that's done as an algorithm. Bob's going to talk about that in more detail. Am I right? Interrupt if you have any questions, or interject if you guys have any clarifications. We good? I was expecting more of y'all to be looking at your code than at me, but thanks for that. So for those that have any numerical sort of inclinations, here's a bit of a numerical algorithm piece. This is taken just the thickness equation and a tracer concentration. Forget the velocity, just assume that's done. So here we get the essential 6 steps of the vertical Lagrangian regrid remap method, okay? So the first step is layer motion via convergence of horizontal advection. Okay, that's given you this W grid. So that's vertical velocity of the grid is just given by the convergence of the horizontal thickness transport. Okay, if you converge, you cause those layers to go apart. If you diverge, the layers get closer together, right? The next step is to do a predictor corrector or a predictor step for the vertical thickness, for the layer thickness, okay, using that grid velocity that we calculated in the first step, okay? And then we use that predictor thickness to get a predictor of the thickness weighted tracer concentration. That's the third step. I'm sorry, my highlighter is not easily. So those steps are the Lagrangian part of the model algorithm. Okay, nothing in there about mapping across surfaces. It's just horizontal convergences and layers moving upward and downward depending on convergence or divergence. The next step is to regrid. And that's a step that is a prescribed step. It is, you are given a prescription for how you want to define your grid, okay? How you want to do your, in this figure that I showed where that blob was moving, we were defining a grid as some rectangular grid that we map back to, okay? That's our target grid. And now, we've moved that grid back, because in the first 3 steps, the grid got contorted. The vertical grid spacing got contorted, and it moved with the fluid. And we may not want the grid to be always moving with the fluid. We have to renormalize. That's the regrid step. And that is by defining this target thickness, which by defining your thicknesses, you effectively define your layer grid positions, your layer interfaces. And that then introduces that movement of the grid doesn't change the state of the fluid, it changes the grid. But by changing the grid, you change where in the fluid state you are representing your fluid state. And so that effectively changes, well, so that doesn't effectively, that just changes the grid. It doesn't change your state. And that step was, for me, the hardest step to conceptualize. The state of the ocean, according to this method, is not evolving when you do the regrid remap stuff. The regrid remap stuff is just changing the grid and changing where in the fluid you are representing the fluid. But because you're doing that, you're moving your grid around, and there's interpolation errors that you might incur, and that in effect leads to truncation errors that can lead to spurious mixing or what have you. But nonetheless, in principle, you're not changing the state at all. You're just changing the representation of the state. So those who've studied physics, it's about a passive versus an active transformation. Okay, this is a passive transformation. You're passively changing the grid, you're not changing the state. All right, that's the regrid remap step. The regrid step is this target grid, and the remapping is when you are updating the representation of the tracer concentration in this particular example. So that, I don't expect everybody, unless you've heard or seen that before, to appreciate those things, but hopefully some of these points will recur to you. It takes some getting used to. It's a very different approach from, say, MIT ROM's MOM5, okay, where you're actually moving, you're actually advecting stuff vertically. So there is a direct analog in the Eulerian approach of this vertical remap stuff. It's just vertical advection, okay? John Dukowitz, in I think 2001, wrote a paper in which he really articulated this connection between the two. But there's a lot of advantages to doing it this way numerically, and that's why it's done this way. Okay, that is a bit on the vertical method. Let me go to the next one. Here is let me type this into the chat, the next slide. Here's a figure that we put into our paper. There's a paper in 2020, Griffies, Adcroft, Hallberg, that talks about the method, if you're interested in it, and James. Here is a picture perspective, a little more detailed picture. Example talking through what I was just talking about. So consider a state of the ocean, vertical Z, horizontal in the X direction, Y direction, what have you. And the colors here represent, say, a temperature field or a density field. And the lines, the dotted lines are the horizontal positions, constant X, and the horizontal solid lines are the constant Z surfaces, for example, constant vertical coordinate. So say you have a wave that comes through, say it's an adiabatic gravity wave or something like that, just a gravity wave. And so the temperature surfaces go up and down now, right? And the coordinate surfaces move with that temperature surface, okay? Temperature is the only equation here. The density is just temperature in this example, okay? So when I say temperature, I mean density. So the coordinate surfaces in the adiabatic or Lagrangian part of the algorithm just follow that wave, okay? Just like an isopycnum model would. All right, and so these coordinate surfaces, the grid surfaces, are contorted with that wave. Okay, the horizontal dotted lines are just fixed. That's the Eulerian part of the model. Okay, so it turns out that you can decide how often you want to go from just following the flow to regridding and remapping. That's a choice, but you have to do it frequently enough that your coordinate surfaces don't overturn on themselves. So the regrid step, the same state, okay, but now instead of the dotted lines being your grid, the solid lines, the solid horizontal lines are your grid. Okay, that's regridding. That's renormalizing your grid. Okay, just imagine this was a turbulent flow and it was non-hydrostatic, for example, and it would overturn. You'd lose your monotonicity of your coordinate system, and therefore you couldn't use that coordinate anymore. So in this case, it's just a linear wave, but let's say we want to regrid to the horizontal now. So that's the regrid step. The remap step takes the state and remaps, and in this example, it's just a linear interpolation of the state to the solid horizontal lines now. Now you see a blurring of the left figure. Now it's a little blurred when you remap because you only have a certain amount of vertical degrees of freedom to do that remapping, and so you lose the truncation. You lose a bit of the resolution through the truncation. That's where the number of vertical layers you have determines your ability to do a good remapping step. When you're remapping algorithm, of course, you want to have a higher order remapping algorithm if you can help it. That's it. And then the final state is you just throw away the old grid and start the time stepping again with the new grid and the new representation of the state. So if you got that, then you've got the essence of the MOM6 algorithm. If you don't got that, then think about it a bit, because I think it's probably something you will get if you think about it enough. It's not that complicated. The complexity is in the details. Conceptually, it's just vertical Lagrangian and then regrid remap. Good? Question? Say that again? Maybe Bob, can you touch on some of those advantages of this?
So there are a couple of them. First one is you can write your code to work with whatever vertical coordinate you want, not tying yourself into anything. Second, we'll get into this later when we get to time stepping. It turns out that there are important parts of this step. Stephen emphasized the tracer, and from a client perspective, that makes a lot of sense. But there are other more rapid dynamics where with this approach, you don't even consider the tracer. Oh, sorry. Thanks, Steve. So there are a couple of huge advantages. The first one is that you've written your model in a completely general way. You're not tying yourself into any vertical coordinate. And so if you have some reason to put more resolution someplace because that's what you're interested in, it's something that you just use a different set of rules for where you're remapping things to, right? You can do anything you want. The second huge advantage is that there are parts of the algorithm, and I'll talk about this later, which are, Steve has emphasized the tracers, but there are other parts of the time stepping, for instance, associated with internal gravity waves, inertial oscillations, and other things. You can deal with those without actually doing anything with the tracers. You're just moving your vertical coordinate around. And that means that the cost per tracer is dramatically lower with this approach than with other traditional models. And as we're looking at Earth system models that have very large numbers of tracers, Cobalt, I think, is up to 36 tracers. Having something where the cost per tracer is a couple of percent, as opposed to in MOM5 when it was about 20%, is a huge savings. It allows us to do science that we couldn't do otherwise. There are some other advantages in terms of your ability to control diapixel mixing, especially from the remapping. The choice of the algorithm for the vertical remapping can have a big advantage. Those are the three that I'd just kind of like to highlight here briefly. We'll get into more of them later when I've given my whole talk.
So that's great. It does add complexity to the algorithm itself, and it does take some thinking about how you're doing stuff. But there's one that Bob did not mention is it allows you to build on the ability of isopycnal models to have layers that vanish, which allows for you to have moving grounding lines with ice shelves, which to me is the thing that I always see as a big advantage with the layered approach over an Eulerian approach. John. So the question was vertical velocity. How do you calculate vertical velocity, or how do you diagnose vertical velocity? There is no vertical velocity in MOM6, but you should, in principle, in my philosophical opinion, be able to diagnose it. And it has been a headache that we have not had that in our code for years. Does Alistair or Bob want to give a more rational, less emotional response to that question?
There are many different places that vertical velocity shows up. From, if you only care about the tracers, the W dot that Steve highlights is the vertical velocity. If you care about the sphere interpolation, which is a dynamic balance between, say, vortex stretching and the change in potential vorticity, that's a different vertical velocity. They're not staggered in the same place. If you care about the net motion of say, an object, that's a combination of the flow across the coordinate surfaces plus the movement of the interfaces. So the challenge here is we can give you one of these vertical velocities, but if you use it the wrong way, you're going to get results that don't make sense, right? So the vertical velocity for the tracers is not the one that you would use for the sphere interpolation. There is an equivalent sphere interpolation. It's just that it's a different vertical velocity. The other challenge that we face in the ocean is the vertical velocity is an unmeasurable quantity, effectively. It's so small that it is something that you can only infer. And so it's something that's very hard to validate against observations.
So that answer doesn't maybe satisfy the ecosystem people that want to look it up well in their boundaries, or the tropical people that want to look it up well in the tropics. And I would say that if you are one of those people and you want to get your hands dirty and prompt some development of diagnostics, then let's do it. Because I think that we've all been hearing we need vertical velocity for a few years, and it's something that I agree with, but you know, it takes some diagnosis. And we had a vertical velocity in a Python script for a while, and we realized after I don't know, 6 months that we were leaving a term off that was important to have. So that turned out not to be a viable approach. I have a bit more about diagnostics. Good. Okay. So that's I'm not looking at the chat. Is anybody? The chat. Okay. I'll look at it. It seems like the vertical resolution is key in the remapping step to get an accurate new state. Is there any recommendation in how to figure out what is sufficient vertical resolution? That's from Alex Hallman. I've done a lot of work on vertical spurious mixing stuff. There is, I mean, we're playing around with resolution now. Anybody? It's a hard question to answer in general. Does Alistair, you want to, you've done the work on the remapping.
So I think Alex is asking about resolution, about where do you put the resolution? So, I mean, the answer is that that's a work in progress. I mean, there's several papers about what resolution is required to represent the dynamics accurately. I'm forgetting the Australian paper.
Yeah, Stewart et al., which I'm on.
Yeah.
It's looking at vertical modes and representation of the vertical structure of modes.
And that was in the context of a Z-coordinate model, right?
Z-coordinate model. Yeah.
So the question of where to put resolution is still a very important one. Thank you, Alex. But you know, it's easy to say, oh, well, we need to put the resolution where there are structures. So, for example, where the thermocline has got higher curvature, and there's lots of changes in density in the vertical, you clearly need lots of resolution to represent those structures. And in the case of some of the tracer fields in biogeochemistry, if you've got lots of strong gradients, you want to put the resolution there. The code, the exercise of generating grids that do that well and do everything else well simultaneously. So do the dynamics well, do the biogeochemistry well, do the thermodynamics well. All of that is actually a hard problem. So there's, you know, it's an industry generating grids in CFD, you know, figuring out how to have these automatic grid generators, adaptive grids, and so on. And we are moving in that direction. We think that that's exactly the sort of thing we need to be doing. But it's stuff that's still a research question. So Alex, the idea right now is trial and error. We basically, the grids we're currently using, we make a guess, we put resolution hopefully in the thermocline and in the mixed layer. And we generally have coarse resolution in the abyss, but not so coarse that we lose ability to resolve anything. And then we try it and then we adjust it. And so right now it's an empirical approach. And we really do want to get to a more objective approach moving forward. But if anyone has ideas about how to go about doing that, that's definitely a good research topic.
Yeah, one of the difficult things with climate modeling, global climate modeling, is that a good vertical coordinate layout density structure is in the North Atlantic is not necessarily good in the Southern Ocean. So you want to represent overflows, you hope to represent overflows with isopycnals, but that may get too deep in some regions or too shallow in some regions. And you incur a lot of spurious mixing and you start to get problems with that. So yeah, it's an ongoing question. Anything else? Wenda. So if it breaks in the overturning sense, that's a non-hydrostatic process, which MOM does not do. And so you have to have a mixing scheme, right? But if you wanted to do Lagrangian, vertical Lagrangian remapping in a non-hydrostatic model, you would have to make sure that you did your renormalization of your grid at fine enough times resolution that you would always have your grid at least monotonic. We're not, but we're a hydrostatic model. So any overturning in the vertical is parametrized, just like hydrostatic models. Okay, diagnostics. So this is now moving to Ralph Dusen's cookbook. This is where I think a lot of users can be really most useful in the world of MOM6. And in fact, this is how a lot of us get involved in MOM6 development ultimately, is by asking questions, writing analysis, and then if then you go deeper and deeper and you say, well, why is it done that way? And you finally start to understand the algorithms. But a lot of people stop at the just output analysis. And so one of the places that I helped push, I guess it's been 5 years ago when I first got into MOM6, was to look at budgeting of tracers. And this is a wiki or documentation that Graham McGilchrist and I put together on documenting the analysis of budgets for tracers, temperature, salinity, biogeochemical tracers. I'm not going to go through in detail, but this is just, what are the terms you want for the heat equation, the salinity equation, the salt equation, thickness equation. One thing that that often people don't appreciate, with a finite volume model, you're time stepping content of tracer. And that by that, I mean, it's an extensive quantity per unit area. So it's salt equation, not the salinity equation. It's the heat equation, not the temperature equation. And I'm being pedantic about it because thickness is involved in that, thickness of a layer. Okay, the budget equations are conservative for layer thickness or layer integrated quantity. Okay, I still see some people saying, I want the temperature equation. Well, then there's a non-conservative term on the right-hand side due to the layer movement that is less convenient from a budgeting perspective. People still look at the temperature equation, but you got to be careful with that particular approach. And part of the confusion is a lot of people come through, or at least they think in sort of rigid lid Z coordinate world where the grid is fixed in space and time. And so the difference between thickness and not thickness weighted has no distinction because the thickness in that world is independent of time and space. Whereas in MOM6, it's fundamentally finite volumed, and you have to work with thickness weighting when you form your budget equations. The other thing that is done, and this was really some work that Graham and Andrew Shao and Alistair and others worked on, was getting these budgets to close on a remapped grid, diagnostic remapped grid. It's good to say that we have a generalized vertical coordinate grid, which is, hunky-dory. It's like, wow, that's so big. That's just something you share to your friends at a cocktail party. But what do you actually want to analyze is often on a fixed vertical coordinate, a fixed grid, something you can look at and compare to something like the World Ocean Atlas. And so we do that regridding diagnostically online every time step. And it took a bit of work to make sure that that was fully conservative and you could get closure of your budgets in the regridded space. Now, when I say regridded here, this is diagnostic. This is not part of the prognostic equations I was talking about initially, but this is if you want to save your budget terms on your diagnostic grid, you need to do that online conservatively. And that's been done as far as I know. I mean, we continue to find little pieces that are not conserving, but I think we're happy now. Jan Eric, are we okay with it? Yeah, I mean, he's been looking at it most recently for the temperature and salinity equations. So that's important. And we talk about signs and showing the budget closure. Here's an example Python script in Rof's website or in Rof's cookbook that lays it out. And this is now a discussion about diagnostics on the native grid. When we say native, that's the model's prognostic grid, okay, or diagnostic on a diagnostic grid. So here we are, a lot of details in this example. Diagnostic outputs in a user-defined vertical grid. You can define your user grid, and there's a few sort of templates in the code for the user grid. If you have a grid you want to output your diagnostics on that's not in the model, just emulate it. Now there's some questions about monotonicity of that diagnostic grid that we're kind of going backwards and forth with Matthew on something for the AMOC, but I think for most purposes, it's pretty straightforward to input your diagnostic grid. All right, so there's a lot of examples, a whole diag table to save. What are the terms you want to save out? There's not like a parameter says save budget terms, true. You got to go in and put these terms into your diag table. Okay. So because the save budget terms true is sort of a nice thought, but these terms are coming from different modules. And so you would have to pass a lot of logicals through different modules that becomes clumsy. So it's best to just, at least so far, we've taken the diag table approach. Diagnostic table, diagnostic manager part of FMS used by MOM6 is actually pretty sophisticated and very flexible amongst the codes that I've seen around the world for other diagnostics. So make use of it, push it, find problems with it, limitations, and help develop better ways to do it if you find ways. So that's tracers, simple scalar fields. Momentum. Let me paste this into the chat. This is another cookbook that Rof has that I helped write with Hemant Khatri, a former postdoc, now at Imperial. At Liverpool. We are interested in the depth integrated vorticity, but to do that, we needed to have the momentum budget terms. And that was something that took a bit of work. These are easier said than done. Yeah, the model time steps these equations, but saving these terms when you have split explicit time stepping, when you have thicknesses that vanish, it just takes some, getting your head into Hallberg's head and figuring out what he was doing. And that's tough. So, but we did it. As far as I know, we've got a closed budget for the velocity equation. And here are the terms for the diagnostic names that we put into the diag table. Coriolis, velocity, nonlinear Coriolis, kinetic energy, pressure acceleration, baroclinic, barotropic. I mean, that's where things get subtle, because the model is split explicit in the if you don't know what that means, you're time stepping the fast gravity waves with very small time steps, and then the slower baroclinic motions are time step with a longer time step. And there's a compatibility that Bob worked out 10 or so years ago to make sure that everything is compatible and stable. And it was quite an achievement because others had done it and they did it poorly until Bob wrote that paper. I guess it was 2009. Is that right? So these are the terms you would save if you're interested in the momentum equation. And there's some notes. And so then if you want to do the vorticity of the vertically integrated or the barotropic vorticity that people use the term, you have to integrate or sum these equations in the vertical. And that's what we do We do that in the code. We save these vertically integrated terms online in the code because you really want, with these budget equations, you really want as high a accuracy or high a precision as possible. To do a lot of this stuff, say, oh, let's just save the terms and do it offline, you're going to have problems with closure of your budgets, and things are going to get more noisy than they otherwise would be. So you really want to try to do as much budgeting, much of the calculation of these diagnostic online as possible. That's been my experience over many years of doing these things. So here's the term. I can't, oh yeah. And yeah, here's the math term in the middle column, and here's the diagnostic name that you would put into the diag table for MOM6 on the right column. And here's the words of what it is. And so here's an example with Python script. Hamant wrote, looking at various terms: pressure, acceleration, vertical remapping term, stress from the winds, horizontal viscosity term, other terms. So one thing that's philosophically important to appreciate, budgets are like drinking from a fire hose. You need to, it's tough. You say you have a science question, you want to think, oh, what's the important process here? Well, it's important in my mind to start from having left-hand side equals right-hand side. Left-hand side being your time tendency, right-hand side being all the different processes. When you're at that point where your budget closes diagnostically, then you can see clearly what are the important terms, and then sort of check your theory. Okay, it's geostrophic balance, what have you. If you don't have a good closure, there's always that nagging question in your mind. Well, if you change the climate, are you missing something fundamental? You know, if it's in this residual that you'll often see, oh, it's just 10%. Well, that's not a big, well, in some cases it can be, if you look at regions, some of these residuals can be important. So it's really, really useful to start with, and then you throw away terms once you have all the terms laid out in front of you. Don't start throwing away terms before you know they're small. And that's why we've spent a lot of time documenting and testing and fretting over non-closed budgets. So that's the velocity equation. So the final one is taking that, and Hamant and I wrote this on vorticity. If you're interested in vorticity, the depth integrated vorticity. This is now taking those momentum terms, taking the curl of the depth integrated velocity equation to form the vorticity equation, the depth integrated vorticity equation. And here is the table of what you would need in words: the process, the math term here, and on the right-hand side is the diagnostic you would save in the code to do that. And so this is where you will save the diagnostics, and then you'll have to do your Python scripting to combine them to do the curl offline. We don't do the curl in the code. You have to do it here. Here's your diagnostic calculations. The beta term, the V depth integrated velocity times beta to give you the meridional transport by planetary beta. You have to calculate beta times that VMO 2D. The wind stress curl, you just take the curl of the wind stress. The bottom pressure, or the bottom the bottom drag term, and then you calculate the nonlinear terms and bring them all together. And here is the diagnostic equation, and here's a Python script with examples of these terms. It's not a small script, and here you go. That's your barotropic vorticity terms in MOM6. It was not easy because there's some subtle points, and there's two papers that I'm editing, one that just got accepted by the British using Nemo, about the subtleties of the barotropic vorticity equation and bottom topography, stuff like that. A lot, because you're taking derivatives and things get noisy and closure, and we're not time stepping a vorticity equation in any of these primitive equation models. They're primitive equation models. They're time stepping the velocity or whatever. We're not time stepping vorticity. And so when you diagnose vorticity, you tend to get a lot of noise, number one, and you tend to not close your budgets very well, number two. And so there's still research out there on model diagnostics of barotropic vorticity balance. So that's my spiel. I hope I didn't offend anybody too much. And hopefully you got something from this. So again, you as users, you're probably not going to be changing the model algorithm too much unless you get into numerical methods. You're going to be using the model, trying to get output and make sense of that output in a rational mechanical sense. And you're going to be looking at diagnostics. And hopefully you'll say something that nobody's done before, and you'll put in a new diagnostic to help do that. That's where you can contribute more easily and less intrusively as a developer by putting in a new diagnostic. If you're not changing the answers at the bit level, very few people care, as long as it's cleanly put in and it's not, not put in a kind of in a hacky way. You have to think about how you code it, but that's really where users can become very, very valuable. All right. Any questions? All right. Online, Bob, you have a follow-up?
I have one comment. You've noted that the thickness is in meters. That's true in the Boussinesq form of the equations. MOM6 can also be run as a non-Boussinesq model, in which case the units of the thickness are kilograms per meter squared. It's a mass-based unit, so that the equations are all the same. It's just that you reinterpret what h is. There are some places where you also have some heights, some interface heights associated with, for instance, the gradient of geopotential height. That always stays in meters. So that's one subtlety in the equations that we didn't go into, but it's one where when you get used to it, it gives you a very easy way to flip back and forth between Boussinesq and non-Boussinesq forms of the equations. And some of the diagnostics, even though they're calculated internally in a mass unit, you can write out some of the diagnostics in meters instead, or in kilograms per meter squared going the other way.
Great. All right.
Okay, thank you, Steve.